Hello, my name is Kyle Dampier, and today I'm going to be talking about my project, Surgery Simulator. So on the agenda today, I'm going to do a project walkthrough, and talk about what my project is actually about. Then I'm going to show you how I plan to test it and how I actually did test it eventually. Then I'm going to talk about Monai, some of the problems I faced, and why I had to have such a big switch right at the end of my project. And finally, I'm going to be talking about how I actually did the integration within Unity, and then after that, we're going to finally get to the demo. So first, the project walkthrough. So processing medical imaging data is extremely crucial to the success of a doctor's surgery. So current solutions try and project 3D images onto 2D screens. However, that requires the doctor to have to gain a 3D understanding by taking the 2D version of it and making it easier and like translating it into a 3D sort of thing in their head. Labeling structures like livers and bones can be time consuming, but it's oftentimes pretty necessary if a doctor wants to do a sort of accurate surgery or diagnosis. And since a surgeon and doctor's times are extremely valuable, any amount of time we can help the doctor save is also extremely valuable. So the solution for this was to combine both of these problems into one intuitive software package. So currently this is what the DICOM scan sort of import screen looks like. This is a project that I've kind of came onto. This is not a new project that I've started. This is actually a research project that's been going on for years. And this is an example of what a doctor would look like when they're trying to paint or change the label of a scan. So here's an example of the pipeline. So you first have the scan, then you have the actual VR model, and then from there, in VR, it's a lot easier to actually do these sort of draw out and have like a sort of 3D brush that you can use to label the voxels. And then finally you can export it, and then eventually you'll be able to simulate the patient itself from the scan. So my job in this whole entire project was to take the first couple parts of the scan's VR model and do that label segmentation sort of automatically, which saves a lot of time for the doctor and makes the program a lot more valuable to them, because they also have to spend time switching from their previous program that they're used to and know to this new program. So here's the plan for testing. There's two main ways to compare model performance in terms of 3D segmentation. The first one is Dice similarity coefficient. This essentially evaluates the performance of the reproducibility of manual segmentations and the actual spatial overlap of the accuracy. So what does that mean? Essentially, it's just how, for each class, how many of the classes, how many of those did you get correct, and of the ones you got wrong, how similar are they to the other labels, and it weights that sort of accordingly. So typically, this is applied to help show that a model is reproducible, and it's almost a score of accuracy for a segmentation model. And this basically takes each pixel and performs a cross-validation on the expected input and the predicted output. This is typically combined with K-fold, which is a way to split the data set up into 5, train the model on 4 of the 5, and then evaluate the model on 1 of the 5, but you do that 5 times. So you essentially have 5 different models you're training, 5 different evaluations. The second one is mean intersection over union. This takes into account the region common to both and computes the percentage similarity, which is a little different because it doesn't take into account the similarity of the actual classes themselves. This is extremely effective on segmentations with multiple classes. So this is just a visualization of what it looks like. I also provide a visualization of Dice similarity coefficient. So as you can see, the Dice similarity coefficient is is a little bit different than a mean intersection over union. However, it is different, and it is a different score, and it does provide a little bit more of an accurate score. However, it is harder to compute. So another check that we have to do is making sure that we have the quadrants correct, like so like say you're looking in VR and the label is different than the scan or the actual data that you're supposed to look at. So we have to make sure that they line up in the scan that I give her and the labels that I send her back. So that's just a check that I have to do on my part. Lastly, so MonoEye. So to start out this project, I wanted to create my own segmentation model, completely custom. And I'd found a data set, and this was the data set that I had found. The images are stored in an NII.gz format, which is standard for most medical imaging data sets, especially CT and MRI. This contains these labels, and there's 140 labeled CT scans, and this is the paper that this data set came from. So first of all, it has incomplete data. So this is the label percentages. So like as you can see, the number of slices in each of it. So like the number of slices is if a slice is like a photo or two-dimensional photo of one part of the body, a slice is one photo, and then there's a bunch of slices. So essentially, the data set that I found, and I couldn't find a lot of data sets that were better than this one. In fact, this was the best one I could really find that had really varying number of slices, and that's bad for a model because when you're training a model, especially one that's a volumetric segmentation, you want to have a predefined size for the slices and whatnot. And so I had started cleaning out the data, and it improved my accuracy and my dice score a little bit, but it didn't really improve it enough to where, and we'll get on to Monai later. But as you can see, the label percentages, so zero being background label, so you can see most of it's not even labeled, most of it's background. 1, 2, and 3 are all different types of labels, and as you can see, the standard error or the black line is extremely off for a lot of these. So it's hard for me to actually use this data set for a model that would be used in the real world. So here's the percentage of data labeled background. So you can see, this is a distribution of all the stuff in my data set, and that's just the percentage of what data was labeled background. And this is the percentage of data labeled liver. So you can see it's better, it's a lot better, but it's not very good. Same with bladder. Bladder had a lot of scans that just didn't have bladder. So it was hard to actually predict bladder. Lungs was also really good. Lungs had a very good data representation. Kidney was terrible. Kidney had barely any data points that had kidney. Bone, same thing there. But eventually I came across this tool called Monai. So Monai is essentially a open source library for that doctors can use to do exactly what I was trying to do, was create segmentations of the image. So something that's great about this is that it's open source. That means that anybody can use it. You can go in and copy the code and do whatever you want to it. It's standardized, which means that if the visualization works for one model, it'll likely work for all the other models, which is great in our use case because not everybody's going to be doing the same thing. It's user friendly. It has a great way to sort of interact with the API, and Monai also has a really large focus on reproducibility. What does this mean? Well, they basically give you a way to look at the data sets and figure out and download the data sets and retrain the model based off the data set from the research paper. So a lot of these models that are coming out are from research papers, and so a lot of doctors or a lot of people trying to reproduce the results, it's a lot easier to do so when you actually have the data to reproduce the results. So Monai is just a really cool and awesome way for doctors to build a community around AI and medical imaging. It's super easy to sort of integrate with, and that's what I focused on, and it's extremely high quality. So the software that they have is so standardized, it's very good, and it's I would trust using these models in the real world, simply because they're extremely good tools, and these segmentations I'm creating aren't necessarily going to be the final segmentation. They're just something to help the doctor, and I think these models have a good enough accuracy to do so. And talking about standardization, they also offer something called a model zoo, which allows you to essentially do segmentation or classification on any type of data that you want, and it just works out of the box, which I think is amazing. So the one that I focused on was the full body segmentation model. This had a lot of classes, and it was extremely accurate. In fact, its dice score was close to 99.8%, which is insane. However, the model requires a massive GPU, and I just quite simply did not have a GPU to be able to test it. And I couldn't test it on HipperGator because, well, I could get it working on HipperGator, but I couldn't get the demo working with it on HipperGator because HipperGator has very closed networking, which means I couldn't run a VR system and connect it to the Monai system because there was no way to form a connection between my computer and the computer on HipperGator. So yeah, when I tried to run it on my computer, it says so. It already had 7.16 gigabytes already allocated. That was probably from the VR system that was running, and it tried to allocate 6.55 more, but it couldn't because and I have a great GPU. My GPU couldn't handle everything that was going on. And that's kind of why I'm doing this. I'll show you guys a demo in Slicer, but my computer was already dying trying to get the VR system and the models running at the same time on my really good system. I didn't. I didn't. I tried to record for the demo, and it was extremely difficult for my computer. So essentially, how I plan to solve this was we split the models for an MVP. In order to make it more accessible to hospitals, we can basically have models that specialize in certain tasks. So I talked to my leader or my advisor, and she had told me that she wants certain things. She wants the rigid body, some of the rigid body structures and some of the soft body structures. To which I found a smaller model that does some soft body segmentation, so some partial with results. So you can see that this is just an example of a soft body segmentation. The performance on this, so the dice during training is higher than 90%, which is still incredibly good, not as good as the other one. It's a loss during training. You can see it starts to converge, which is exactly what we want to see in a model. And its dice scoring validation is one of the most important things. And as you can see, it actually outperforms on the validation than it does on the training, which is an incredibly good sign for a good model. The vertebrae pipeline with results. So this is like a rigid body segmentation. This is like the back or the vertebrae. So this is the performance. So you can see that a bunch of other researchers have run it on their own data sets, and they have all gotten similar results, which is a great way to show you that this model is actually generalizing and understanding what is going on inside of that MRI or CT scan. So finally, the Unity integration. So the Unity and Python lifestyle diagram looks something like this, where the doctor uploads the files, and so when the doctor starts the program, it starts both the Python the Python server and the Unity application. From there, the Unity and Python application do a ping pong, where they sort of make a connection. That allows Unity to ensure that there's actually something there, and Python to tell Unity what's actually available in the model. So Unity then is able to save the scan that they upload in a file system, and then it sends the file path and everything that they need to process the scan, like what they actually want, and Python does all the pre-processing and the segmentation on its own, and then it creates a whole new file, and then that file is then sent back to Unity, and she can actually visualize it in Unity. So thank you. So to my demo. So the demo for today, and hopefully I'll be able to edit this. So let's stop. Okay, again, I couldn't get the VR system working at the same time as even the small models because it's just a lot for the computer to handle, and my GPU only has so much VRAM that it can run it in the same system. But here's an example in 3D Slicer that I've gotten to run. So if I go, so you have to just go and install the Monai label thing, which you guys hopefully wouldn't have to do this if you're trying to run it. But essentially, Monai allows you to get the next sample. So just get the next one. So let's do a better one. So like this one here. So when I refresh this, it basically gets all the models and everything that are available. So let's run the deep edit segmentation first. Hopefully my recording doesn't crash. Please. So as you can see, the segmentation is right here. So you can see if I were to go in this one here, you can see that it's segmented out those that soft body portion. So same thing here. If I wanted to do the vertebrae pipeline, and there's a bunch of pipelines that you can choose from, but this one might crash my computer. Okay, we're back. There it is. So hopefully I just speed it up, but here is the segmentation of the actual vertebrae or bones. So here they are together. So I wanted to get this done for an MVP. I just wanted to have an example for her to be able to get this data from a Monai API. And you can see the Monai API running at localhost 8080 or 8000. So this standardized API just allows you to do whatever you want, and it gives you documentation on how to actually run the models itself. So yeah, I think that's about it. I wish I could show you it on VR, but I couldn't get the model running at the same time, which we're gonna hopefully figure out by the time the demo comes out on GitHub, but thank you for watching.